Hello everyone, this is Super CEO, and finally today we will have a look at questions from the enrichment slash challenge questions from the textbook on continuous variable. So as usual, let me throw this statement in from Cambridge. Okay, so the two questions that I want to have a look at today from enrichment slash challenge questions are these ones, question 9 and question 10. Okay. All right, so question 1. So as usual, first you're going to have to show that this given little f of x, the frequency function, is a PDF. So this time though, the interesting thing about this um, domain for this function, as I circled here, noted here, is that there's a lower limit, but there's no upper limit for the domain. In other words, x starts from 1, but goes all the way up to, if you like, infinity. Okay, so that's something to note, to make a note of. Now, as usual, x to the 4 is greater than 0, so therefore 3 over x to the 4, which is that function, is definitely greater than 0 for all values of x, as long as it's greater than or equal to 1. So that's the first condition satisfied. Then the next one is the integral on that domain. So as I say, there's no upper bound, so it's like taking the integration from 1 to infinity. But mathematically, infinity is not a number. It's the status of a number is getting bigger and bigger even as we speak. So what we're going to do, the mathematicians will do a little trick, is just convert that and take the limit. Okay, so in other words, you think of a number that is greater than 1, let's call that m, and integrate this between 1 and m, and then you take the limit of that integration, which is the same thing as saying taking the limit from 1 to infinity on that frequency function. So if you perform that, remember all the while here the capital M is a positive number bigger than 1. So perform the usual integration, then that gets evaluated from 1 to m. But here in my primitive function, I've got the negative in front, and I hate dealing with the negatives. So what I'm going to do is a little trick, is that you swap the order and then drop the negative sign. Not the negative on the index, but negative as the coefficient of the variable x. So drop that and then swap the order. So then you get this. Okay. So substitute 1, then you get 1, and 1 on m cubed. Okay, now have a look at this. Yes, we're asked to find the limit of the sum, but individually, the limit of 1 is still 1 as m goes to infinity, because it's just a constant, so it doesn't really matter. And the limit of this 1 on m cubed is going to be, think about it, the numerator is fixed, yet the denominator is getting bigger and bigger as you take m go to infinity. So that whole fraction becomes 0. So individually, the limits exist. So therefore, the limit of the sums is the same as sum of the limits. So that's 1, and that's obviously 0. So it's 1 minus 1 is 0. Sorry, 1 minus 0 is 1. So therefore, the second condition is satisfied. Hence, this little f of x, even though the domain is unbound, is a fair income PDF concluded. And part B, you're asked to find the expected value between 1 and infinity. So remember, it's the x times the little f of x. So it's this. So as usual, take the usual integration exercise and take the limit. Instead of 1 to infinity, you go 1 to m, and m goes to infinity. So again, I have the negative sign popped up. So drop that and then swap the order. Then that's this. Okay. So then if you evaluate this, again, I'm skipping a step here. So I can see that individual limits exist. So I'm just going to do the argument saying the limit of the sum is the same thing as the sum of the limits. So if you put the 1 in there, it's going to be 3 on 2. So that's 3 on 2, even after you take the limit. And the limit of 1 on 3 over 2m squared. So as you notice that as m gets bigger and bigger, the whole fraction becomes almost insignificant. So that's basically 0. That limit is 0. So 3 on 2 take away 0 is 3 on 2. So that's the expected value. All right, next one is the variance. So variance is x squared times that integral of x squared times the frequency function, and then take away the square of the expected value, or the average that we got from here. Okay, so nice little index law says that's x to the negative 2 and minus 9 on 4, because that was 3 on 2 initially. So that means now the first term is the limit of that after the integration. Minus 9 on 4 stays the same, and that's just now 3 on x, 1 to m, because I've got the negative in the previous working line. So drop the negative sign, swap the order. That's exactly what I'm doing here. And minus 9 on 4. See, that's now, if you substitute 1 in there for x, it's going to be 3 on 1, 3. So that's a constant, so the limit's there. And if you put m there, and as m gets bigger and bigger, 3 on m is basically 0. So individual limits exist, so therefore limit of the sum is the same as the sum of the limits. So using that argument again, you're going to get 3 minus limit of 3 on m, take away 9 on 4. So these first two terms come from that evaluation, okay? And take away 9 on 4. That limit becomes 0, so that's 3 on 4 is the variance, which is sigma squared. So if you now take the positive square root, that becomes the standard deviation, okay? All right, part C of the question 9. This is now the actual probability. X continuous variable less than or equal to 4, which is the same as x less than 4, strictly less than 4. That's from 1 to 4. Why? Because remember the lower bound was 1, so it's 1 to 4. So evaluate all that. That should be an easy exercise. So that's 63 on 64. Very, very high probability. It's almost 1, okay? X greater than 2. So that's the same. Using the complementary idea, it's the 1 minus p x less than 2. So that's 1 minus 1 to 2. Take the integral of that, then you get this. Okay. Again, I'm doing two things here. That's going to have a negative, right? But notice I swapped the order so that I can only deal with a positive primitive. That negative comes from that one. It's got nothing to do with the negative coefficient of the primitive function. I've taken that into account by swapping those two. From 1 to 2, I'm now saying 2 to 1, and drop the negative, okay? That's 1 on x cubed. So if you do that, then you get 1 on 8, okay? Probability between 2 to 5, it's obviously x less than 5 take away x less than 2. Now we've already worked it out, so that's from here, so that's, which is this, so I'm just taking that one. X less than 5, again the primitive is, sorry, the integrand is the same, but the limiting values are different, 1 to 5 instead of 1 to 2. So again, same argument, again the dropping the negative sign and swap the order, then you get this, then that, and at this point you can use your calculator to get that, okay? And part D is the cumulative function, or CDF. I always forget what the D stands for. It's is it distributive, or cumulative distribution function? Yeah, okay, whatever. CDF. Okay, so CDF is now, by definition, is continuous variable less than or equal to a random number x. So it's going from 1 to x. Again, the lower bound originally the domain starts from 1. So 1 to a random x. What that means is your x in the integrand now gets replaced as a parameter called t. Okay, so that's, and therefore it's you can only integrate it with respect to t. So that's that, and it's 1 on t cubed. Again, you should have negative, but again, I hate working with the negative in the primitive, so what I do is drop the negative and swap the order of the integration. So that's what I do, and that's the CDF. Okay. All right. Question 10. Again, if you have forgotten what the question 10 was, it's this. All right. So a lot of differentiation questions, as well as the application of EX and variance of X. Okay. So part A, so you're asked to find the derivative of X e to the X. Obviously, you're going to have to use the product rule. So like I said here, product rule being applied, then you get this. And therefore, x e to the minus x, making that guy, this term, the subject. So you move that one over, that stays, and that term now shifts. So that's this. Okay. Hence, if I integrate this on the left-hand side, I have to also integrate the right-hand side term by term. So that's going to be the integral of e to the minus x dx. But this second term on the right-hand side gets interesting because have a look at this. What you do is you first of all differentiate that and then you integrate it back. So you get back to where you started. Okay. Now so that's what I mean by here. Differentiation followed by integration will get back to the starting point. You differentiate and then you get it back up. So you basically are where you started with. Okay. So then you get this. Now, of course, if you can't still see that straight away, then follow this argument. So just focusing on that second term on the right hand side, then it's this. But notice here, dx and that dx, you can think of this as a fraction times an integer. It's like, 5 on 2 times 2, and 2 and 2 there, both of those get cancelled, so you get this. And what I'm claiming is this is the same thing as x e to the x, e to the minus x plus c, because you can think of this x e to the minus x as one big x. Okay, like this, then that it's now, that's 1 times dx integrated is x plus c. Or if you can't see it, use the smaller letter like du or dx, d little x. Then we all know that it's just u or x plus c. So that's exactly the same. Remember, x e to the minus x, you will treat that as if it's a big letter x. So then you spit back this big letter x, which is x e to the minus x. That's another way of thinking of it. Then you get that. Okay. Very good. And part B, you're asked to find the expected value. So that's x times the frequency function. So you get this. Now, that is based on the result from part A, which is what we just did in part A. So that's negative. And because it's this time we're dealing with the definite integral, you don't need to worry about the integration constant, okay? Because they get cancelled anyway. So then you just focus on the first two terms. All right, so that's this, getting evaluated from 0 to negative, 0 to infinity, but I've got negative. So as usual, drop the negative sign and swap the order, which is this, but at the same time, I'm factorizing as well. Okay, so then that means replace the infinity by m and take the limit as m goes to, obviously, infinity. So that's this. Put the 0, then you get 1 because e to the 0 and 1 plus 0 is 1. So 1 times 1 is 1. And again, individual limits exist because that's 1. And if you put m in there, and you will note it, I'm going to explain it here further, but 1 on m over e to the m as m goes to infinity, that's actually the limit becomes 0. Why? Well, let me take you to the decimals. Okay. And if I graph those two, so this here, the blue line is obviously y equals x plus 1 or m plus 1. And this red curve is e to the x or e to the m if you like. But what happens as m goes to infinity? Well, the rate at which the exponential function grows outweighs the rate at which this straight line increases. I'm not talking about in the vicinity here of x equals 0, but x gets really large far out here. The exponential function actually outpaces the straight line. So therefore, remember the original function is straight line over that. So as m gets really bigger, remember this bottom, the denominator outruns or outpaces or overwhelms the growth in the straight line. So therefore the whole thing becomes 0 because the denominator gets bigger and bigger. So it's 1 minus 0, hence that's just 1. So in other words, the expected value for this function, believe it or not, is 1. Okay, now question 10. Sorry, still question, question 10. Now part C of the question 10, you're asked to find the derivative of this whole of this, all of this 3 terms. So that's, for this one, you're going to have to do product rule, okay, twice. So, on the first term, you do the product rule, and this one, I take the 2 out, and then I'm going to leave it like that, okay? All right, because that's actually from part A, yeah? So, derivative of x e to the minus x. So you don't have to do the product rule again. So I'm going to just take the result from part A. That's why I left it there, and that's now the third term differentiated. So then you get this, and this one, like I've made a little mention there, it's this from there to there, that's the direct result from part A. Okay, so a bit of cancelling, which is the fun part, then you get minus x squared e to the minus x. Okay, so all of this, okay, just one term, minus x squared e to the minus x. Therefore, if I integrate this, then again, integrate that and integrate this, differentiate and integrate it, then you get back to where you started with, which is that, okay? Differentiate and then integrate, so you get this one back entirely the same. Why the negative in front? Because you've got negative in front of all of this. So it's like bottom-mass. You have to deal with this inside, what's happening inside here, and then you multiply everything by negative, then you get this. And don't forget the integration constant, okay? All right, so now we needed this to work out the variance of x, because if you work out the variance, it's x squared times the frequency function and take away square of the mu, or the expected value. Now when you do that, that's why you need this, okay, result before. So which is this? So the primitive of that is all of this, okay, evaluated from 0 to infinity. But all of these 3 terms has negative, meaning I can take the negative out as a common factor. But as you know me, I hate working with the negative, especially in the primitive functions. So I'm going to drop the negative sign, and what that means is I'm going to have to swap the original order of integration. So that's that one. And now take the limits from m to 0, and m goes to infinity. Okay, so of course individual limits exist, so therefore limit of the sum is the same as sum of the limits. So apply that argument. If you put the 0, luckily it's got all the x terms in it in the first 2 terms, so that's going to be 0, 0, and then here it's 2 to the 2 times e to the 0, which is 1. So that's where you get the 2 from. Now take away the limit of all of these values evaluated at x equals m, which is this, m squared on e to the m, blah, blah, blah. Okay, now notice here, again, even though this is quadratic, we now know that exponential growth outpaces the quadratic as well. So we know that as m gets bigger and bigger, this whole thing becomes 0 because the denominator gets even bigger, okay? Same, that's linear, so that's no match at all. So that's still 0. That's a constant, so that's even worse. So this thing becomes 0 a lot faster than the other 2. So that's all of these 3 is 0. So 2, take away 0, and then take away 1 gives you 1 as the variance. And that is it, believe it or not. So I hope you enjoyed the video with the much more challenging questions. And then I'll see you guys next time. Bye.